Chapter 9, Unit 2. Let's talk about assumptions of the t-test. You're going to have independent observations. Again, the values in the sample must consist of independent observations. This is the same as a z-test. And you must have normality. The population sampled must be normal, same as a z-test. This assumption, however, for the t-test can be violated, and it won't matter, but this can only work if there is a large sample size. For a t-test, the larger the sample, the smaller the error, and more likely you will be to produce significant results. The smaller the variance, the more likely you're going to have significant results. So you want a large sample and you want a small variance for the results to be significant. If the variance is too large, that means the scores are widely scattered and it's very hard to find patterns. So here's an example. Researchers report that reading from a light-emitting e-reader before bedtime can significantly affect sleep and lower alertness the next morning. To test this finding, a researcher obtains a sample of 9 volunteers who agree to spend at least 15 minutes using an e-reader during the hour before sleeping and then take a standardized cognitive alertness test the next morning. For the general population, scores on the test average a mean of 50 and form a normal distribution. The sample of research participants had an average score of M equals 46 with SS equal to 162. Using an alpha level of 0.05 and a two-tailed test, is this sample significant? So step 1 is going to be writing your hypotheses. Remember, there's both. There's a null hypothesis and the research hypothesis. So for a two-tailed test, the null hypothesis would just be the mean is equal to 50. And the research hypothesis would be the mean is not equal to 50. Step 2, you're given n equals 9, so you have to find the degrees of freedom. So that would be n minus 1, you get 8. And then you're going to go to your table. So you're going to look at the degrees of freedom equals 8 row. You're going to look at alpha 0.05 two-tail, and you're going to look down in that row, and you're going to find the critical values of plus and minus 2.306. Remember, it's plus and minus because it's a two-tailed test. You have to add that in. So draw your picture. Step 3 is going to be to do your calculations. So again, you have to start with variance. So you can find that because they gave you sum of squares and they gave you n. So you get variance of 20.25. Then you're going to find estimated standard error. Plug in your variance and your n, and you should get 1.5. Then you can find your t-score. Your t is equal to m minus mu over the estimated standard error. This gives you negative 2.67. So you're going to put an x on the graph, indicating where your calculated t is. And step 4, you're going to reject the null because there is a significant treatment effect because you're in the rejection regions. Let's talk about how to report the results of a t-test. You would say there is a tendency for the level of alertness to be changed after reading a screen before bedtime. You would say T of 8, and 8 in parentheses is the degrees of freedom that you used on the table. So you have to show them what degrees of freedom you used. And then you put your answer, negative 2.67. That's your calculated t-score. And then the probability is less than 0.05 because you're in the rejection regions and 0.05 is your alpha level. And it's a two-tailed test, so you don't have to write two-tail. Note the degrees of freedom always goes in parentheses above, so it's T of df is equal to T calculated. Again, remember, do not use the critical values that you used in the table for this t-score that you're reporting. You always use the one that you calculated in step 3, and then the p is either less than or greater than the alpha level, depending on if you reject the null, in which case you use less than, or you fail to reject the null, in which case you use greater than. Example 2. To evaluate the effect of a treatment, a sample of n equals 9 is obtained from a population with a mean of 40, and the treatment is administered to the individuals in the sample. After treatment, the sample mean is found to be m equals 33. If the sample had a standard deviation of s equals 9, are the data sufficient to conclude that the treatment has significant effect using a two-tailed test with alpha equal 0.05? So again, step 1 is going to be your hypotheses. Remember, you have to have both. So your research hypothesis says the mean equals 40. That's the null hypothesis. The research hypothesis says the mean is not equal to 40. Go ahead and draw your picture. Again, you're going to find the degrees of freedom for step 2. In this case, it should be 8. You're going to use alpha 0.05 two-tail and go to the tables, and you're going to find critical values of 2.306. You're going to calculate estimated standard error, because in this case, you were already given S equals 9. So you're going to use the estimated standard error equation that has S in it, which is S over square root of N. So you're going to find estimated standard error is equal to 3. And then you're going to use the T equation and substitute in what you know, 33 minus 40 over 3. You're going to get negative 2.33. So let's put our X on the graph to indicate where that would be. In step 4, you're going to reject the null. There is a significant treatment effect. How do you report these results? You just say there is a significant treatment effect. T of 8 is equal to negative 2.33, and the probability is less than 0.05. All right, learning check problem 1. A sample of n equals 25 scores is selected from a population with a mean of 73, and a treatment is administered to the sample. After treatment, the sample has a mean of 70 and an S squared equal to 100. If a hypothesis with a T statistic is used to evaluate the treatment effect, then what value will be obtained for the T statistic? Well, let's solve the problem. They told you that your sample variance was 100, so you can go straight into finding your estimated standard error. Use the equation that has variance, which is square root of S squared over N. You should find an estimated standard error of 2. Then you should be able to put that into the T equation and find a T equal to negative 1.5. And there's your answer, C. T would equal to negative 1.5. Let's look at learning check problem 2. A hypothesis test produces a T statistic of T equals 2.3. If the researcher is using a two-tailed test with alpha equal 0.05, how large does the sample have to be in order to reject the null hypothesis? Well, let's look at the first one. If n is 8, that means degrees of freedom is 7. And if you look at your table, using two-tail alpha 0.05 for degrees of 7, you get critical values of 2.365. Okay? And if you're told that your test has a T of 2.3, that's what they calculated, put it on the graph, it would not be significant, so you would not reject the null. So the answer would not be A. All right, let's look at B. If you had at least n equals 9, this gives degrees of freedom of 8. Go back to your tables. This time you get 2.306. But your calculated t-score they gave you is 2.3, so you are still not in the critical region. So you're not big enough yet. Let's look at n equals 10. This gives degrees of freedom of 9, and if you look in the table, you get critical values of 2.262. Finally, we're here. The calculated t of 2.3 is larger than 2.262, so now we're finally in the critical region. So you would need to have at least n equals 10. That's how large the sample would have to be. If you wanted to go ahead and solve for n equals 11, you'd get your critical values, and it would still be in the critical zone. But your answer for this problem would be C. You'd need at least a sample of 10 in order to be able to reject the null hypothesis. Learning check problem 3. A sample is selected from a population and a treatment is administered to the sample. For a hypothesis test with a T statistic, if there is a 5-point difference between the sample mean and the original population mean, which set of sample characteristics is most likely to lead to a decision that there is a significant treatment? The answer would be a small variance and a large sample.